Hello, everyone. My name is Alberto Nieto, and I want to welcome you to the most recent session of the How to Do Map Stuff series. We're going to be talking about wrangling data, visualizing patterns with Python and GIS. And as has become custom these days, in every email header, I sincerely hope you're doing well during these uncertain times or during these confusing times or challenging times, however we want to say. I really want to thank you for your time, for being here. It's really great to just simply get together again and talk about the things that inspire us and keep us going, right? I also want to thank Daniel Huffman, who took the chance to coordinate this big event for everyone. He's done an amazing job wrangling all of us. So, in the spirit of wrangling a lot of people, we're going to talk about wrangling some data. So, what do I mean by wrangling? Um, Really, if we look at this dictionary definition of data wrangling, it's a little bit cold. It talks about a process of transforming and mapping data from one raw data form into another, etc. But really, what I want to call your attention to is this inspiring view of this cowboy or cowgirl really herding all of these different entities together to do something useful or something needed. And this is in the spirit of what many people have to do before you put together a map, right? Before, very often we see these beautiful maps or these perfect examples of spatial analysis. And very often we also ignore a little bit of the work that it took to get there before we even show that. All the work that we have to do with data, preparing it, cleaning it, interrogating it, sometimes failing. Sometimes data just flat out is not appropriate for the map that we're trying to make. So very often you spend a lot of time doing that. And I think it's necessary to talk a little bit about that. I also want to give a brief caveat that I don't particularly consider myself a strong cartographer, but I do work a lot with data. So I think the position here is I'd like to share with you some tools for data wrangling before you get to that map stage. And particularly what I want to highlight is three components. Python, certainly. We're going to talk about Python not just as a scripting tool to automate things, but really to interrogate data, to quickly set up these steps so that if you're processing data on a daily basis, you can quickly use that and continue working with that. GIS, certainly. I think a lot of us geographers work with GIS, whether it's desktop or cloud, etc. But GIS very often gives us a good view of the data from an exploration standpoint, right? Simply putting your features on a map already tells you quite a bit about your data, but then interrogating it for patterns, interrogating it for different stories that your data may be able to tell you before you really get to the map making stage. I think that exercise of just exploring is quite important, right? And having strong GIS skills and also good software is also very helpful. And then the last piece that I'll briefly dive into is spatial statistics. The idea there is that there's a lot of tools that really help you explore your data or wrangle your data and kind of interrogate it in different ways that kind of give you a better case for the map that you're about to make. So really what we're going to cover today over the next really 45 minutes or so is a few examples that I put together. And before the current COVID-19 crisis, I really believe that what most people were going to be thinking about this year was the US presidential election, right? And this is not to bring politics or those crazy things into this topic. It's really just to talk about this common goal of getting people to participate in the election process. So what I want to show you is um, one data set that we really started to wrangle, and that particular data set is for county presidential election returns, all the way from 2000 through 2016. The idea here is that regardless of which party you're affiliated with, which viewpoints you favor, participating in the election process is quite important, especially in a country like the United States, where voting is completely voluntary. And actually, voter participation is relatively low compared to a lot of other countries. So in a dynamic sense, every year you get new voter participation data. You have a lot of new data that you can process and turn into maps that inform I wanted to take a chance at looking at the most recent election and evaluating how voter participation had occurred and maybe infer some things about the upcoming election. So in that sense, I'm opening up here a desktop GIS. What I wanted to do is bring that data using Python and work with that data using basically a Jupyter notebook. And a Jupyter notebook, for many of you may have already worked with them. Many of you may just be starting to work with it. I think hopefully this can help regardless of your viewpoint there. But the idea here is that if you're writing Python, a Jupyter notebook can be really powerful to simply prototype a new workflow. So let's create a notebook here. So this is a brand new notebook. Really the way it works is you can write Python code. So I'm going to do a print statement. Hello, everyone. Happy to see you today. And execute that. That's a contained snippet of code. I can write another set of code on the next cell, and these two cells are discrete from each other. I can execute cell 1, cell 2, or cell 2 and then cell 1. And that idea of having these little separated modules of code that I can test option A, option B, that becomes really powerful when you're starting to prototype one workflow and you're not really sure where you're going to take your analysis or your data wrangling. You're just testing things. Another reason why notebooks are quite important is because I can write descriptive text. So this is a code cell, but if we change the type of cell to be markdown, we can actually write some description. So here is where I will download the data and then write my code to get my data, blah, 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 blah. So this can be a really powerful tool if you're sharing essentially a workflow with someone else. If you think about classes that are now taught for Python or for scripting or for data science in general, a lot of classes teach their entire lessons in Jupyter Notebooks, and it's because it's very easy to wrap up an entire lesson through descriptive markdown text as well as code that actually does what the markdown text says it will do. And one more thing is Jupyter Notebooks are really good for visualizing data. So if I want to take an Excel spreadsheet or a CSV of data for election returns and visualize it in a Jupyter Notebook, I can simply show the table. So let's get right into it. I have a completed notebook here. I'm going to dock some of these windows so that we can kind of see a little bit more of it. And I am going to go through some Python code, and I don't expect you to be fully up to speed with code. It's okay if you're just learning Python, or some of you may already fully know Python, and this may be pretty elementary. But I hope everyone takes a little bit from this, and even if we skip certain lines of code, it's okay if you don't remember them. We can share this notebook afterwards, or we can really, the idea is just to give you the concept of Python as a good way to do data wrangling. Um, so what we're doing here is we're basically taking that data that I showed you for voter turnout in presidential elections. I downloaded the CSV from the MIT election, basically this web page right here, the MIT Election Data Science Lab. And the way that data looks, it's basically we have a few columns. We have the year of the election, the state, the county, the FIPS for the county. We have the office. All of them are for presidential elections. And then the candidate and the party. So the way it works is each county, if we actually sort by this, so if we actually look at each county, you have several records for each county, and basically have what we want to have is a data set where each county is represented once in this table so that we can actually create a map and start looking at some of the structure of that data. So let's get started. And really the way we're going to conduct this is in 3 steps, even though it's going to get a little bit complex down the line. Just think of it as 3 generic steps. The first one is to load and clean this election data. The second one is to geo-enable the election data. Essentially, we're going to geocode those counties. And then the third one is going to be to enrich it. So if we have those counties and we now have election data, in many cases, we may want to do some analysis to determine if low voter participation is tied to a specific demographic or to a specific condition for the people that live there or some event for the people that live there, right? So let's start with step 1. I'm going to walk through this a little slow at first, and then I'm going to speed up. And I'm going to try to explain each cell as we go along. So the first cell uh, has import statements. And these import statements, if you're used to Python, you will probably see them in every script you work with. But the idea behind an import statement is that you can bring tools that other people have created in Python. So I created a new cell here. I wrote import requests. Request happens to be a module or a set of tools that someone wrote to help us do a request to a web page. I don't need to build a tool to request data from a web page from scratch because there's been a lot of brilliant people that have written these tools and we can simply leverage them, bring them into our Python script and do that. So in this case, we're bringing in 4 sets of modules. We're going to bring in a module called ArcGIS that helps us connect to a web GIS and bring data essentially from ArcGIS Online. We're going to bring in a tool called Pandas. If you're working with Python and data, Pandas is a must know. I definitely cannot emphasize that enough. Pandas is a utility to essentially work with data in a format that I've heard described as Excel in Python, and I think that can be quite appropriate. It lets you do a lot of the operations that you would typically do through Excel, but it's so much more, as I'm hoping to show you today. OS is operating system, so if you need to change directory or create a folder, delete a file, create a file, OS has a lot of utilities that help you with that. And finally, ArcPy. ArcPy is a lot of desktop GIS tools. So if you're trying to do geocoding, for example, we can do that through ArcPy. Or if we want to do some spatial statistics function to determine hotspots, we can use ArcPy in that sense. So I did Shift Enter to execute that cell, and it's basically going to import all of these tools, and we can keep going. So the next cell right over here has some reference to that CSV. I have the same file that I showed you in the same directory as the Python script that we're executing here. So I can simply point it to the path, to the name of the file. And right here, we're going to invoke pandas. We brought it as a variable called PD. So we can simply, let me give you some hints that I love to share every time we do Python. One of them is that if you don't know what a tool does, what a module does, you can enter the name of the module as you've established it and then do period tab. And what that gives you is essentially a view of all the different classes and methods in that tool. And it lets you scroll through them up or down. Now, this is essentially just akin to exploring all the different subtools of the pandas module. So there's subtools for regarding to date time, for creating data frames, and a data frame is essentially what we want. A data frame is just a view of that CSV in Python memory. So the way we're going to create that data frame is by invoking pd.readCSV to read a CSV and passing in our table path. And we're also going to pass some additional parameters here. The additional parameter is going to be to interpret. Oh yeah, I see in the chat that the font is quite small. Let me see if I can zoom in a tiny bit. I hope I can. Let's see if I can do this. Hopefully that's a little bit better. Yeah, we'll try that. And if that doesn't work too well, then I can maybe revert that. I apologize if the font is a little bit small. I'll try to describe it in a little bit of better detail. So there's a little bit of a delay between what I see in the stream and what I'm showing. So I'm just confirming that that doing this didn't break the stream. Okay, it seems like it's proceeding okay. So at this point, what we're trying to do, and I am going to actually zoom back out. I apologize. It was a little bit hard to see once I zoomed in. I'll try to zoom in when we get into details. So maybe let's do that. I'll kind of scroll down and then we'll zoom in a little bit closer so that people can see a bit more. So what we're going to do here, let me go ahead and zoom in again, is basically we are going to read the CSV that we've established into a data frame. And we're going to show the head of the data frame, essentially the first 5 records or so of the data frame in this Jupyter notebook. And that's one of the things that I was really emphasizing, that you can see your data through the notebook. And it's quite different from other scripting environments where you essentially just have a Python file and you execute it. and hopefully that worked. And maybe you see the data at the very end by loading it into Excel or something like that. Here you can kind of have a pretty close relationship with the data, see what you're doing each step along the way, right? So let's keep going. The next part that I want to share with you is how we actually start handling some issues with the data. So the first one is quite simple. Some of the data is missing. There's going to be records that have some null values in the total votes field, or maybe null values in one of the other fields. And what can we do with Python to handle that? So let's go ahead and zoom in right over here. We're going to do a few things. I'm going to set up some variables here, and these will be to simply set up what field we're going to check nulls for. And right after doing that, we're going to determine how many rows are in the table. And then we're going to check how many rows happen to be null, and then do a print statement that gives us a sense of whether that's an issue or not. So I'm going to execute it, and then I'll explain a little bit more. Really, the goal is to provide some basic assessment of how many records in the data don't have values. We're checking the field called FIPS, uh, and our print statement basically tells us that there are 64 records in the CSV that don't have values in FIPS. And that's about 13% of the available data. Great. So that can give us some information on whether we want to maybe impute some values, do some investigation. Why are these FIPS missing? Or maybe we want to simply omit those records if we're trying to quickly prototype a workflow. And the idea here is that, so now going back to the code and explaining the lines, there's a query right here where we have a data df. This is our CSV in Pandas data frame format. We're making a query where we're passing the field to check, and that field to check is called FIPS, and we're running a sub tool in Pandas called .isNull, and that gives us essentially the return records. Let's actually create a cell up here and show you how that works. So we have data df. If I execute that cell, it just gives me the table. If we do let's see, FIPS .isNull and run that function, we get this query where different records may come back as true or false, right? And that can be a mask, that can be a query that we can apply to get records back. So what we can do to get those records back is at the very beginning, we're going to call our data frame and locate, so LOC, and locate where this is true. So now we get only 64 rows where the FIPS field is null, right? That gives us essentially that query for the records that we now are concerned about. And we're doing one more little thing here called .shape. .shape, what it does, let's do it without all this other mumbo jumbo. We're going to just say .shape to get the shape of the data frame, essentially how many records we have versus how many columns we have. And because we care about how many records are in that query, we can do .shape at the end. And if we get .shape at the end, we get the shape of the data frame from that query. And what I'm doing here by passing 0 is basically getting just the first item there, which is how many rows. So 64. So that is assigned to this little variable that says how many rows are null. All of that to do that. But once you get used to it, you kind of start speaking that language of how to query, how to apply those masks, and quickly get a sense of null records in your tables. The other part is right here, we're determining the percentage versus the total. So we have our variable with 64 null records here, and then we have the full row count, which is the shape of the entire data frame. And then we're just going to multiply by 100 to get a percentage. And that's how we get this fancy little print statement, which really isn't too complex, but hopefully that helps you get a sense of what you can do. What I like about it then is, let's say that we wanted to check for null records in a different field. You can simply select one of these cells and copy it. So I'm going to select C and then V to copy it right here below it. And all we need to do now to check on a different field, let's say, I think one of our other fields, if we check our data frame, another field is candidate votes. So let's go to candidate votes here and then simply execute this. Now we've performed all of that function for this other field. We don't need to rewrite the code. We can simply take that code snippet, put it in a new cell, and go through that. So we get the result for candidate votes. That amounts to almost 1% of the data. So we may want to do some imputation there, or take some time to actually bring some interrogation into that field, particularly if we care about it. There's other functions also that you can apply. So not null is the opposite of null. So what we're doing here is essentially removing those records where fibs happens to be null. And now if we look at the shape of this data frame, let's go ahead and do dot shape. 50,460 records, and that was compared to the original tally, which I think was a little bit higher. So if we do that, 50,524, yeah. So in this case, we have gone ahead and removed some records. So let's go ahead and do that one more time to go ahead and remove them. Now, the next step that I want to show you, I'm going to zoom out here to show this little graphic. Data types. So as data comes in into our data frames and into Python, we really care quite a bit about the type of data that we have for each field. For example, this FIPS field is the ID for each county. And the ID for each county can be important. We can use that to join it to another table. We can use it to label. We can use it for obviously quite a few reasons. And it's important for this to be interpreted well, meaning it should be numeric, or actually it should be string rather than numeric. The problem is that it can be interpreted as a number. And if it's interpreted as a number, then there's records that have leading zeros omitted simply because they're considered as numbers. So to fix that, we're going to speed up here just a tiny bit. Uh, let's go ahead and get the first 5 rows of the table. We actually see that problem happening here. The first 5 rows of the table are counties, or is a single county in Alabama, Autauga, and actually one record from a second county called Baldwin. Every FIPS should have 4 or 5 digits. And these have leading zeros truncated because the field came in as string, or actually the table from the web page considered this numerically. So we really had kind of flawed data to begin with. And what we're doing here, I'm going to go a little bit faster here, not go line by line. But the idea here is we want to figure out how much of the data has this issue. Using that print statement logic that we kind of checked for before, we can find that about 10% of the data has truncated FIPS values. So in order to fix that, we can write a function. And in Python, a function can be useful. It's essentially a subtool that you can package up and use for a variety of purposes. We're defining this tool to be called fix trunc zeros, and this tool is going to receive a value as an input. And what we're going to do with this tool is we're going to check if the length of that value as an input is 4 characters, then we're going to append a string 0 to the value and return it. Otherwise, just return the value itself, right? And let's test it. So right here, I've already written a cell to go ahead and basically fix that value. So if we pass a value of 7042, we're going to go ahead and correct that. But if we go ahead and pass a value that has 5 valid records, so 90210, everyone's favorite show from the 90s perhaps, it should keep it the same and not really fix that or do anything to it. So pretty straightforward function, nothing too complex. The idea here is that we can then apply that function to any set of fields. So we're going to apply it right here to the FIPS field, and we're going to call fix truncated zeros and pass every value for every row in that column. And now we have that field corrected. Instead of having 1001, we have 010001. All right, let's keep going. One more bit of code here before we get into some kind of more lighthearted data visualization. And this is really the important one. The table structure is not quite in the format that we want it to be. And what I mean by that is we really, to create a map of voter participation or a map of who voted for which candidate, ideally what we'd like is a table where each record shows a county and different fields have different candidates and their votes. The way it is right now is we basically have each record corresponding to each candidate. So this graphic hopefully shows you what we need to do here. We need to take the table, lock some fields aside, then pivot it. we have to basically twist it and then assign some new field names so that we can keep working with this table. And if that doesn't make immediate sense, I don't blame you because a lot of time basically goes into things like this. But what I want to just elaborate at a high level is that through Python, if you can do this, and what's best is that if you can figure out how to do it once, then you can simply take that logic and apply it for other data sets or other problems in a pretty straightforward way. I'm not going to get too close into the code at this point because it'll take the rest of the time, but I just want to give you a sense of what you can do. So what we're doing here is essentially a few different things. We're going to set some indices, some fields, lock them aside right here. And then we're going to, for the rest of the table, we're going to pivot it using this unstack operation. And what that gives us, if we execute all of this, rename the output columns, and reset the index, it gives us that exact table structure that really helps us make a map. Every field or every record then becomes a county for a particular year. And in case, actually, in this case, we do have several years of elections. We're going to really focus on 2016. But for 2016 alone, we have independents. Each county is represented just once in that table. So at that point, we're able to keep working with that table. Now, I'll share this notebook, and if you're really curious about that cell and how it did it, it really, I think, works better if you're able to kind of sit down with that code, take it one step at a time, test it, make your own cells, and kind of come to speed there. The idea here is just to give you a sense of what you can do. So over here, we would explain essentially what that huge snippet of code did above. We're just going to execute it and get our output table for now. One more thing that I think is quite important is calculating new columns that could make very interesting maps later on. So for instance, we have the votes for the Democrat candidate and we have the votes for the Republican candidate, but we don't have votes for other parties. If we wanted to do that, we do have total votes and we can subtract the Democrat votes plus the GOP votes from that total and assign it to that field votes other. So just like that, we can basically create a new field and apply that operation wholesale. And that's one of the things that is really powerful about pandas, which is that you don't have to loop through each record and do that calculation. Like you don't have to set up a for loop and then do that calc. You simply take your fields and it does the array-wide operation in one sweep, which is really, really good if you're working with really large data sets. And by that same logic, we can just go nuts, right? So there's going to be a lot of other fields that are important for, or could make really interesting maps. For instance, we can calculate the share of votes that went to each party. We can calculate the raw difference in votes between each party or the percent difference between each party. And if you write that logic once, again, the next time the data set is updated, you just apply it to it. So at this point, if we execute that, we now see all these other fields that if you visualize them in an output map for each county, they could become pretty interesting maps to look at. So, okay, that was a lot to throw at you at once, perhaps. For some of you, this is perhaps basic, but I hope that gives you a sense of what you can start doing with Python. The next part I want to do is to geo-enable the election data. I want to bring basically some geometry because all we've been doing is working with that table as Python memory. And we want to actually make maps, right? So this is where the GIS really starts to come to bear. I'm going to create a GIS variable here. So let's go ahead and zoom in again so we can see that. So we have, basically we're calling this ArcGIS module and authenticating with ArcGIS Online. And from there, we can search for content. I'm going to search for content named USA counties. And if we execute this cell, we get that item. This is from something called the Living Atlas, which has a lot of data that you can use that's already pretty cleaned up and really well put together. So another part of data wrangling is finding good data to begin with. Perhaps you don't have to create your data from scratch, right? For these purposes, what I want to do with these counties is bring their geometry, their shape, so that we can add the election data as fields to that shape. And the way we do that is we're going to find that layer from the Living Atlas. And I'm going to create a spatial data frame, essentially a table in Python that retains its geometry, and we can still bring it back into a desktop GIS later on without having to do a lot of fancy stuff. And from that, let's go ahead and process that. It might take a few seconds to process. There it goes. This table, so this is a second table now, has each county, and it also has the shape for each county. And the shape is important. That's the geometry that we care about. And now we're going to merge these two separate tables, the election table and the geometry table. We're going to bring them together and make a layer. The way we do that is by calling pd.merge, pandas.merge, passing it our data frame that we created earlier with the elections and then our county geometry. And we're going to use that FIPS field that we cleaned up so that we can properly do those joins, right? So that is now called the GODF here in our code. And the way that field looks, or that table looks like, is we have all our useful data, all our fields with the election stuff. But then at the very tail end, we have our state, our shape right over here. Hopefully you can see that at this point. So zooming back out, we're going to query just for the year 2016. Since we have a lot of data for several years, I just want to limit it to a single year of elections and query that. And finally, we're going to convert it into a data set that we can map. So all along, you've been looking at pretty gruesome code. I'm going to dock this over here to the right, show our map view. And what we're going to do is execute this cell that has a little bit of information here called, basically we're going to call a module called .spatial and toFeatureClass to create our output layer. So by executing this, it's going to take the table with the geometry and the election data, and using that shape field, it's going to render it here on the map. So it just finished producing this and it gave us the map. Now there's a big issue here. We didn't see this just by looking at the table, but we now see an important issue, which is that there's a hole in our map. We have a county that's missing. And this county, if we do a little bit of interrogation, there's this Census Bureau webpage that talks about changes to counties from 1970 to present. If we scroll down a little bit, it does take some time to interrogate data issues. So I'm going to spare you a little bit and just go right to the point. What we found is that there's a county in South Dakota called Oglala Lakota, and it changed its name and its FIPS code from Shannon County 46113 to Oglala Lakota 46102. Basically a county that had a change of mind in its naming and now doesn't show in our map. So to correct this, how do we do this? First, we can scroll back up in our notebook and go to where we were producing all these tables. So right over here, what I'm going to do is create a markdown cell. We're going to call it Fix Shannon County Mess. So this is going to be a new section where we're going to write a little bit of code to add this correction. Then we're going to create a code cell and zoom in so that we can see what we're about to write here. We're going to query our output data frame, essentially the final state of our data. We're going to check for records where the table and its FIPS code equals 46102, which is what it should be. So the query comes back empty, meaning the current county does not have that FIPS code. If we check for the old FIPS 46113, there's the issue. We have all these records, actually with the correct name, Oglala Lakota, but the old FIPS code, the FIPS code it used to have several years ago. So to correct this, we can add another cell. We can copy this code. Basically, we're going to say, find all the records with 46113 in the code, and then for the FIPS field, write the new value 46102. So it just did that operation. Let's check if we did our job. First, I'm going to copy that code, check once again for the query for records that have the FIPS of 46113. No records come back. That's good, actually, because we changed them, right? And now I'm going to check for 46102. Okay, now we've corrected that data. We have records that have the correct FIPS and the correct county name. Now, to reproduce this feature class, this GIS dataset, since we've added that little snippet of code to correct that, all we have to do is remerge the tables with the shape. So that's right over here. Uh, query for 2016 again, and simply reproduce the feature class. So right over here, it's executing. It's about to give us the new feature class, and hopefully that county is filled in. And yes, we have our filled in hole now corrected. And now you're able to work with this data to keep producing, hopefully, a good map. So all of that is a lot of Python code up front. And if you're new to this, please don't feel intimidated. It becomes easier, I promise you. You just have to try it, essentially. If this is something that you're already accustomed to, hopefully this is a good refresher, or maybe you were able to pick out a few new things from what you saw. What I actually want to go to now is some ways to visualize this data. So right over here, we have our output table. If we go ahead and show this attribute table here, we have each county for 2016. We have all the fields that we calculated earlier for the share of votes that went to each party. But more importantly, we have a calculation of voter turnout, which is how many people went to vote divided by how many people are eligible to vote. And that's what we care about in this problem. The mission of this whole work is really to produce a map that helps us understand voter turnout. So the first thing I want to do is visualize some distributions of these different fields. I want to see how really should we symbolize this data. So one of the things that we can do is create a chart, a histogram chart to see the distribution of one of those fields. And right over here, I'm going to configure this chart, passing it a field, and the field that we care about in our case is voter turnout. And for voter turnout, we essentially see right away that there's this nice normal distribution to voter turnout. A lot of people are right around this middle range of about, or a lot of counties rather, are between around 55% to about, let's see if we actually show the standard deviations. Really, a lot of people are between 50% and maybe 70%, or a lot of counties are in that range. The majority of counties are in that range. But there are some counties kind of here in the bottom where there's very low voter participation, and some counties up here where there's pretty high voter participation. So while clicking on the chart and seeing them on the map is pretty neat, we probably want to represent that right away in the map, right? So we can quickly simply change the symbology to represent this value. And what I want to do here is create some graduated colors. By default, it'll choose one of the fields and a default color scheme. I don't particularly like this red color scheme by default, so I'm going to quickly change it to a different color. And instead of showing where votes for the Democratic Party are high or low, we're going to select where voter turnout is high or low. And the useful thing is because we saw that this is kind of this normal distribution, most people are right around the average with a few really high, a few really high, or really low rather, we can actually find another color scheme that really maybe is more well suited to a normal distribution with high values and low values. So I'm going to select something like this. Yeah, there we go. And for the method, instead of the default of breaking the different classes by natural breaks, I'm going to use standard deviation because this data is normally distributed. So that is actually pretty appropriate. And through that, through this histogram, through this chart, we can now start to see a little bit of a story here, right? The counties in purple have generally pretty low voter turnout. The counties in green have generally pretty high voter turnout. And more importantly, the counties that are in dark green are outliers for really high voter turnout, and the counties in dark purple are really outliers for very low voter turnout. And from this, we can start to kind of really see our data for different stories it can tell. One thing that I like to create is a bar chart of all the states and the average voter turnout for each state. So I'm going to create a bar chart here really quick, selecting the state as the category. I'm going to select, actually, instead of the mean, we're going to select the median. And for the median, we're also going to tell it use the voter turnout number, and then we're going to sort it in descending values. So what this can now tell us at a high level is quite a few things. So if you look at this map, the purple counties, the counties with low voter turnout, you can almost pick out states just from looking at those. Like Tennessee to me stands out almost entirely without even looking at state outlines. And what you can do in this bar chart now is look at the median value and select that entire state here to interrogate it. So the top 5 states by median voter turnout happen to be Colorado, New Hampshire, a lot of states up in the Northeast, Minnesota, which historically has been known to have really high civic participation. Washington State, I think, is also up there, etc. And by the same measure, you can also look at some states where there's generally pretty low voter turnout, and you can start to sort of stratify your data into different groups, right? The states with low, the states with high. The other thing, though, is if you really look at states, generally, yeah, the state falls into either high voter turnout or low voter turnout. Like Colorado has generally really good participation, same with Minnesota. But there's some states that have kind of this really interesting, deeper story, like Texas. There are some counties that have pretty low voter turnout, some counties with really high voter turnout, some counties with really low. So this bar chart doesn't really tell the full story for Texas. If we select Texas, it kind of just gives us the full median value. So instead of the bar chart, what we can do is use a box plot. So I'm going to create a box plot here. And for the box plot, we can go ahead and tell it use voter turnout. And for the category, use states. So what does this do? The box plot, it gives us a sense of the distribution of values for each state. So for example, for Alabama, the average or about the median voter turnout value for Alabama is about 58%. If you recall, for the whole country, the average was right around 59%, so it's a little bit lower than average. But there's some long tails. There's some areas where voter turnout is actually pretty good and where voter turnout is pretty low. And if we configure this chart, we can actually see outliers too. So there's a little checkbox here where I can select which to actually show me the outliers that fall outside of some standard deviation. And for example, Texas, that one state that seems pretty interesting to me, just looking at this. Texas is right here. If we select it, we see most of the state kind of falls within this box and whiskers. The average is actually pretty low, or the median is pretty low, about 52%. But there's some outliers here. And these outliers, I can just select those in the chart and we can see the counties that those outliers represent. So if you start to uncover these interesting potential stories that could make pretty good maps on their own, why are these counties voting in such great proportion compared to the rest of Texas? That sounds pretty interesting. The other thing you can start to do also is start linking charts together. So what I'm going to do is create one more chart, call this a bar chart for counties. Instead of looking at states, we're going to look at individual counties. So I'm going to select our category as county, and then I'm going to tell that the value it should be concerned with is voter turnout. And we're going to stack rank it from, let's go from y-axis descending, and just have it match the symbology of the map. Whoops. There we go. So it's a lot of counties, so this chart isn't particularly useful, but what we can do now is if we're looking at the map on the top left, the box chart on the top right, and this full view at the bottom, we can set a filter that reacts to the other charts. So for example, let's take a look at Texas. So there's Texas. We've selected Texas. This chart at the bottom has this filter that now shows us just the distribution for the counties in my selection. Another state that I thought was pretty interesting is Georgia. So let's take a look. I think Georgia's right over here. Yeah. Georgia has this tremendous outlier. If we zoom into Georgia, you see there's this one little county right here called Chattahoochee County. Chattahoochee County is particularly interesting because if we do a little bit of research, Chattahoochee County corresponds to, let me change our view here a little bit and show you the map. I'm going to change our base map to OpenStreetMap. So here's Chattahoochee County with its really low voter participation, the lowest voter participation in the entire country. And if we turn off this layer, it actually happens to coincide with Fort Benning, Georgia. Basically, the entire county is a military site. And there's this interesting blog post called "The County Where Almost Nobody Votes." And it's all about Chattahoochee County. And it was interesting just to see it through the data, through the map, through the charts, through the outliers, just that one data point highlighting it as a very discrete entity and just finding this blog post kind of telling us why. And it's really there's a number of reasons. There's soldiers that don't live there. They may vote in their home district or in their home county, and they really just work there. And then there's also a number of other reasons that this blog post cites. But this can be, I think the point here is that as you're interrogating your data, you've cleaned it up through Python or through some other means, and now you're exploring it. You start to find these really individual stories that I think can, on their own, make interesting maps. So from there, I think really where the natural progression that I believe you can take is you're starting to find these patterns for high and low voter participation. You're starting to find these individual stories. The next question to me is why? Why is there low voter participation? Why is there high voter participation? So that brings to bear this notion of enriching data with demographic variables and then checking for relationships. So the way you can enrich data, there are several tools out in GIS that can do this, right? The idea is that for each county, we may have things like, so let me go ahead and pass our input here. We may have things like the different breakouts for age. So if we look at age, we may want to see, okay, what is the median age for that county? Or maybe we want to look at income. What is the average income in that county? So I'm going to get per capita income. Another thing that literature and voter participation really talks about is um, uh, we have age, we have income, education. Educational attainment happens to be really correlated with voter turnout in many cases. So bringing in a few variables that may be associated, such as having a high school diploma, having a bachelor's degree, or a professional degree. It's not that we're saying that they are the cause, but it is interesting to explore relationships and therefore do an analysis and go a bit further. And maybe we want to choose the rate rather than the raw count so that we can do that. So once you do that and you run the tool, you can enrich essentially for every record. You would get a tally of the total amount of people that have or the percentage of people that have a professional degree, the per capita income, the median age, etc. I've already enriched it just to save a little bit of time. We have median age, per capita income, high school dropouts, so people that went to high school but didn't earn a diploma. And just for fun, there's a variable called owning a selfie stick, if you can believe it. So making a map of people that own selfie sticks, I think, is quite interesting. Maybe not useful. Maybe useful for some other purpose, right? Maybe another session. But long story short, what I want to do here now is explore these relationships. How do people with high per capita income relate to voter turnout? Does that have a factor? So another type of chart that we can create is a scatter plot. And I know this is getting pretty into the weeds with different visualizations, but I just find them fascinating. I hope you do too. What we're going to do here is basically tell it, give me the voter turnout in one axis and give me the field that I care about in the other axis, so per capita income. And it's going to bring in the symbology from the map, which I think is pretty useful. And from that symbology, if we look at it, these are the standard deviations. Um, what we can do is basically look at the R squared. The R squared, you don't need to know a lot about statistics, but I can summarize it for you. It's a quantification of how related these two things are. In this case, presumably, the higher the voter turnout, there's some chance that the higher the per capita income, or vice versa. And what I'd like to do is we can set an extent filter so that it only gives us a chart for whatever we're looking at in the map. So at the national level, the R squared is about 0.34. The scale is 0 to 1. If you have a 1, you're perfectly correlated. If you have a 0, there's no relationship at all. So 34 is not that high, or 0.34 is not really that related. However, if we change the extent and set up that as a filter and we zoom into some place like Florida, you actually see that the relationship just in Florida between per capita income and voter participation is much stronger. It goes all the way up to 0.63, like double. So really this, in my view, this is great for us geographers, right? This proves the point that you can't just be a statistician or a data scientist without knowing geography, without knowing location and how that affects different relationships and different parts of your data. Interestingly, as I pan around the map, you see this relationship change down here. It may be a little bit small, but you see R squared's decreasing. So I want to end with one more thing. And this is, while it's interesting to explore the map and pan around and look at the relationship this way, it's a little bit ineffective to answer the question, okay, how is per capita income related to voter turnout? So the final thing I want to show you is a tool. And this tool, what it does is it basically checks for relationships between two variables for a specific county. It first determines if the relationship is statistically significant. And if it is statistically significant, then tell me what type of relationship is it? Is it positive? Is it negative? Is it parabolic, etc.? So I'm going to run the tool. The tool is called local bivariate relationships. And the way this tool works is we're going to pass it our input features. We're going to tell it what variable is your dependent variable. Basically, what do you care about in your analysis? So we care about voter turnout. And then the variable that's going to potentially explain voter turnout is going to be one of those demographic variables like per capita income. And then I'm going to change our output coordinate system to be the same as the map and run the tool. So what happens then is for every feature we're going to create, for every county, it creates this little neighborhood around the county. I can show you really quick through these slides. So essentially what's happening is that there's good relationships, things where one variable is really associated with another variable. The more one value increases, the more the other value increases as well. Or it could be a parabola or a sinusoidal or some other type of relationship. But you may also have these null relationships where there's no good association between the two things. And what's interesting is that there's this thing called entropy that is really good at measuring those relationships. At a high level, the way it works is that, for instance, you may have this variable with low entropy where things are fairly predictable. It's not exactly like this, but I think it helps us wrap our mind a little bit. You may be able to predict where any given point here in this little graphic will be in a few seconds because it's pretty stable and it has low entropy. But if we increase the entropy, or if we increase how much variability there is in that variable, then it's a lot harder to predict. You can't really tell me where these points are going to be at any given time, right? So the fascinating thing is that in statistics, there's a theory that can check whether the chaos between these two variables is shared, whether you may in fact have shared information between these two. They call that mutual information or information gain. And the tool behind the scenes essentially checks for that. If we pass a voter turnout on the left, per capita income on the right, it's going to check for cases where information is actually shared and those two things are statistically significant in their relationship. What's important there too is that it also checks for things that are not just linearly correlated. If the relationship is really complex, like sinusoidal or some type of other order besides just linear, entropy can be really good to do that. So the way it does it is through something called minimum spanning trees behind the scenes. You don't need to know this. This is just to kind of give you the conceptualization behind it. And the tool here just gave us the output. It summarizes, it gives us this map of relationships. And take a look at the legend here on the far left. I'm going to zoom in just for a second. Everything is basically, hopefully I can show this. Sorry, my zoom in is a little bit strange. There we go. Every county then is either a positive linear relationship, that high voter turnout has high per capita income, or negative linear, low voter turnout, low voter income, or actually low voter turnout, high per capita income, basically a different relationship that could be useful, or concave or convex, or maybe too complex to even show. So what does this map tell us? This map starts to get at some notion that if you really care about voter turnout, the areas in pink have high per capita income and high voter turnout, and that is statistically significant. That relationship is statistically significant. So if I click one of these counties, it gives me a sense of the neighborhood around the county and that relationship and why it was statistically significant. And if you're doing further analysis, let's say you're getting into modeling, if you want to predict voter turnout for the next election, you may want to, and you consider using per capita income, you may want to just focus on the areas in pink if you happen to use per capita income as a factor, right? The areas in white or gray are not significant, meaning that the relationship between those two variables really is not helpful to predict or to try to associate anything meaningful there. So this can be quite useful just to get a sense of where those relationships are strong. If you're doing more analysis, maybe you subset your regions. And we kind of proved that point true that we saw earlier. In Florida, there's really strong correlation between your income and presumably your participation in a presidential election. In Georgia, those relationships are actually fairly robust as well, but not quite as much as Florida. Um, so that is a lot to throw at you. I really just wanted to wrap up with a view of these three tools: Python, GIS, and charting and visualizations, and a little bit of spatial statistics there at the end with that tool, just to give you a sense of a lot of different things you can do as you're getting your data ready for all the beautiful maps that a lot of other people today will be sharing with you. Again, I want to really thank you for the time, and I sincerely hope you're doing well during all of these chaotic events that are happening in the world today. But I feel quite confident that us as geographers, we have a role to play here, right? And hopefully we get to see other work that other people are doing. We may have a few minutes here for questions, but again, thank you so much. So let me take a look at our chat. I'm brand new to this YouTube studio environment, so let me see if I can process all of these questions. We actually have a lot of content to go through in just about 2 minutes, so maybe let me go from the top to the bottom and address a few questions. And if you have any other questions, I can provide my email in the comments here. So there's some questions. I assume notebooks used in Pro use ArcGIS Pro Python environment, which means you must have installed pandas, requests, and other libraries separately, or do they come with it now? Um, Generally speaking, the way it works is when you start a Python notebook in ArcGIS Pro, there's a lot of libraries that are already included. If we go to Python in ArcGIS Pro, you can actually take a look at all the packages that come included with that Python environment. It may take a second to refresh my package information because I was installing some stuff right before the session. Probably not a good practice, but there it goes. Really, what I would suggest is if you care about which libraries you have installed and you're using ArcGIS Pro, go to Python. You can take a look at these. If you want to install a new package, you can basically add a package here, search for it. Let's say you're working with Bokeh, which is a really good library to create charts. You can find it here, select that, install it. I actually happen to have it installed already. Or there's also environments, and we didn't get into that. I think that's better left for another session, but these can be places where you kind of have a set of tools already prepared, and maybe you don't want to conflict another project's set of tools. So environments are really good workbenches, in my view, to kind of organize your different work. Um, Maybe we have room for one more question. Let's see. I'm going to scroll down a little bit and see if I can answer a question about the charting. Yeah, I see Philip Pierdomenico saying, wow, I see a clear pattern of low voter turnout in the Appalachians. I did too. It'd be interesting to understand why that is, right? I'm not sure if you can, let's see, I'm reading more. Would you consider making more content? Is there any recording of this video? Yes, maybe I can wrap up with this since it's now 2 p.m. This video, actually, this live session, will be basically recorded and it's actually part of YouTube now. As soon as I stop the stream, you can go back to the same exact link and rewatch it from the beginning and see all of the gritty Python content that we created and our zooming in, zooming out, etc. And also, I'll share the notebook that we created as a link on the comments. I'll just package it up into a GitHub repository. If you want to follow that content particularly, you can download that notebook and work with it there. So we're 1 minute over time. I don't want to steal from other people's sessions. Thank you all so much. I really appreciate you being here. I hope you're having a great time at home and that you're safe and healthy. And hopefully we can all get together someday in the near future. Have a great day.